Chemistry, we are now moving into our first in several lessons dealing with chemical bonds. So the 90 natural elements on the periodic table combine to form millions, actually tens of millions or hundreds of millions of compounds. Chemical bonds are central to chemistry because they are how atoms are joined to create new compounds. Even so, there are only three ways elements combine. The first we'll study are ionic bonds. An atom passes electrons to another atom. Covalent bonds, atoms share electrons. And metallic bonds, electrons jump from atom to atom like frogs on lily pads. So ionic bonds result when an atom transfers an electron to another atom. So there you saw the electron jump from the lithium to the fluorine. That essentially is the whole lesson right there. That's what an ionic bond is. The atom that lost the electron becomes a positively charged cation, and the atom that gained the electron becomes a negatively charged anion. The positively and negatively charged atoms or ions attract each other and form an ionic bond. So ionic bonds must be electrically neutral. So they're made of two ions, but when they join together, the overall structure must be electrically neutral. Ionic bonds create a cubic structure, not always cubic, but often so, called a crystal lattice structure. The smallest unit of a crystal lattice structure is called a unit cell or formula unit. Lithium fluoride, what you see there, is an example of a formula unit. The strength of bonds in a crystal lattice structure is called its lattice energy. Two factors affect the strength of the lattice bond energy. One, the charge on the ion. So a 2 plus charge would be stronger than a 1 plus charge, and a 2 minus charge would be stronger than a 1 minus. And two, the size of the ions. Smaller ions higher up on the periodic table have greater bond strength than larger ions. So let's look at some examples. Charge is more significant than size. That's the number one is more important than number two. So rank the ions from the strongest to the weakest lattice energy. So here we go. There's the four choices there. So the strongest is going to be beryllium oxide, because beryllium has a 2 plus, oxygen has a 2 minus charge, and it's very high up on the periodic table, both of those elements, and therefore they're very small. Next would be magnesium sulfide. They also have a 2 plus and 2 minus charge. However, they're both down in the third row, and therefore they're a little bit bigger than beryllium oxide, so their lattice energy is not quite as strong. Next, we have sodium chloride, that's table salt. Now, those have weaker charges, a 1 plus and a 1 minus charge, and they're also in the third row, but because of the charge, they're weaker than both BeO or MgS. And finally is potassium bromide. They both have a 1 plus and 1 minus charge, but they're down in the fourth row, so they're not as strong as sodium chloride. So ionic bonds form crystal lattice structures. Table salt, sodium chloride, has the formula NaCl. There is one sodium atom for each chlorine atom. The blue Cl is attached to 4 sodium atoms. It doesn't belong to any one of the NAs that's around it. So when you look at that one down there, so NaCl is called a formula unit or unit cell because it identifies that there's one sodium for each chlorine. A formula unit is not a separate structure. So you see the Cl flashing there, that blue one, that's attached to all 4 of the sodiums around it. And really it's a 3-dimensional structure. So there's really another Na sodium in front of it and one behind it that you can't see. Okay, so a formula unit defines the smallest basic unit of a crystal lattice structure. but it is not a separate structure. By repeating the formula unit, in this case NaCl, the entire crystal structure can be repeated. So you see how that salt crystal there is made up of NaCl repeated. So this NaCl is like a single unit of that, and if you keep repeating the unit cell, you create the entire structure. So a formula unit is like an apartment in an apartment building. An apartment can be distinguished from other apartments, but is not a separate structure that can move independently like a car. So you see that apartment in the yellow box. You can tell that one from all the others. So if you took the floor plan for that particular apartment and kept repeating it, you would have the entire apartment building. But you can't pull that one apartment away from the apartment building. Okay, so the green here, the alkaline metals, alkaline earth metals, or transition metals, or other metals, lose electrons and become cations. So they become positively charged. Okay, those are the metalloids. Now the blue, the nonmetals, gain electrons and they become anions. So noble gases are inert, which means they do not bond. Okay, when lithium and fluorine get together, lithium gives up its one valence electron to fluorine. So watch what happens here. The lithium has a low ionization energy, which means it easily gives up its second orbital electron to become a cation. The fluorine has a high electronegativity, so it wants to pull in an electron to become an anion. So you see the electron jump from the lithium over to the fluorine. Now the second orbital of lithium disappears, and now lithium has a full valence orbital, its first orbital, and fluorine has a full second orbital, that's its valence orbital. So the negative charge and the positive charge are attracted to each other to form a bond. This is an ionic bond because it is formed by two ions. Lithium is a positively charged cation, and because it has one more proton than electron. Fluorine is a negatively charged anion, negative ant, because it has one more electron than proton. Notice that ionic bonds follow the octet rule. Lithium's valence orbital, which is now its first orbital, is full, and fluorine's valence orbital is also full, so both are at their most energetically favorable state. Now, ionic bonds happen between a metal and a nonmetal. So there's 6 steps to this that you should memorize. The high electronegativity of a nonmetal pulls on the electron of a metal. So you see that diagram over there on the right. The low ionization energy of the metal means it easily gives up electrons. The electron is passed from metal to nonmetal, like you see on the diagram. The metal, the weak guy, loses an electron and becomes a positive cation. The nonmetal strong guy gains an electron and becomes a negative anion. And finally, the cation and anion both fulfill the octet rule and are attracted to each other to form an ionic bond, as you see down below. Okay, so go ahead and please memorize those. Here's how to create an ionic compound with proper subscripts. So 1, use the charge number of ions or the 60 common ion sheet to assign the charge number to the ion. 2, use the crossing arrows method to assign the subscripts and remove any signs. So let's look at some examples. Okay, and then reduce the subscripts if they have a common factor. So let's start with sodium and bromine. So you take the 1 plus of the sodium and the 1 minus of the bromine, you cross the arrows, and you get Na1Br1, but you don't write the 1s. So that's sodium bromide. Next we'll do potassium oxide. Potassium has a 1 plus charge, oxygen has, so you cross the arrows and you get K2O. In other words, it needs 2 1 plus charges to balance the 1 2 minus charge. Next we have beryllium and selenium. So it's Be2 plus and selenium 2 minus. You cross the arrows, and you get Be2Se2, which you reduce it, like reducing a fraction, and it becomes Bese, because there's one beryllium for every one selenium. Okay, and finally we have iron and nitrogen. So iron can have more than one charge, so you have to know which charge you're using. In this case, we're using iron 2 plus, and nitrogen always has a 3 minus charge, so when you cross the arrows, you get Fe3N2. Now, we talked about this, but atomic radius and ionic radius are different. So let's look at this here. So fluorine has a smaller atomic radius than lithium because it has more protons that exert a stronger pull on the valence electron. So we've seen this before. Now after lithium passes its second orbital electron, it loses its second orbital, making it much smaller. So you see the lithium became much smaller. Okay. After the fluorine receives the electron, the repulsion of the additional electron pushes the second orbital outward and increases the radius of the atom. Actually, we should say radius of the ion. So finally, in summary, a lithium atom is larger than a fluorine atom. However, a fluorine ion is larger than a lithium ion. All right, and that takes care of this lesson on ionic bonds.